So this is lecture 2. In lecture 2, we will discuss the counter design. So there are actually two types of counter designs are there, synchronous and asynchronous. First, we will discuss synchronous counter design using D flip-flop. Okay. So first, I will introduce where we are using this counter. Okay. Counter. Now we can consider a parking system. So an automated parking system here, we want to count the number of vehicles, or we need to open the gate based on the capacity. Okay. For example, here you can see one entrance. Okay. At the entrance, each vehicle will enter in this particular way, and this is the exit. When vehicles enter into the region, you need to count like one. Okay. When the second vehicles come, it should be two and 3, and when it reaches to see here, you can see that maximum it can accommodate maybe 5 cars. Okay, so when it reaches 5, so here you need to indicate a red light. Okay, and when one vehicle goes out of this exit region, again you can decrease the count to 4, then you can indicate light green, because vehicle can enter into this particular. Anyway, we need a counting system, automatic counting system, up counting and down counting. Okay. Here I mentioned this particular counting system by using a decimal system, but in digital system we cannot directly implement this decimal counting system, but we can use a binary counting. For example, if you use two binary bits, you can count 0, 0, 0, 1, 1, 0, 1, 1. So by using 2 bits, you can count up to 4. Similarly, if it is a 3 bits, you can count up from 0, 0, 0, 0, 0, 1, 0, 1, 0 up to 1, 1, 1. You will get 8, 0 to 7, you can count. Here it is 0 to 3. Or at least you can indicate from 0 to 3 or 0 to 7. So this is the basic concept where we are using one of the application where we are using a counter. Okay, and in order to implement this, see, we need a different kind of sensors. So at the entrance, you can see that sensor 1 and sensor 2. So these two sensor we can transmit some kind of signals. Okay, assume that when there is no vehicle, there is a signal, and here you will get an output high signal. Okay, and when there is a vehicle enter into this connection will break, the signal will break, and your signal goes low. And when the vehicle leaves to different region, and when it passes this particular area, again the signal goes to high. Okay, such kind of a transmitter receiver section you can plan at each gate. So here you can see that when the vehicle passes, you will get an active low, and when there is no vehicle, this is an active high signal. When there is a vehicle moving in the particular region, you will get an active low. So from this particular waveform, you can see that you need to count this low region, or you can say when there is a high to low region, we need to count. Okay, that's something similar to your clock signal. Okay, when using a counter, we'll actually count this transitions. Either it's low to high transition or high to low transition. So such devices are normally known as the counters. Okay. The same thing here, when a high to low transition occurs, we need to increment at the first stage entrance part, and when there is the same sensor we are implementing in the exit part, we need to down count. Okay, so initially if the value is 4, we need to decrease to 3. Again, when there is one more high to low transition, it should decrement to 2. Okay. Such kind of operation we need to perform. So this is one of the application of counter, and counters are mainly classified in digital electronics under two categories. One is known as asynchronous counter and synchronous counter. And as the name suggests, asynchronous counter means is also known as a ripple counter, that we'll discuss later. First flip-flop, for example, flip-flops are the building blocks to implement this counters. So for example, there is 3 flip-flops. Okay, this is flip-flop 1, flip-flop 2, and flip-flop 3. So based on the way they are clocked. In the case of asynchronous counter, first flip-flop is connected by using a clock or your signal from the sensor, and the second flip-flop is connected by using the output of the first one. In this way, if you are using the clock, this is known as asynchronous counter. Okay, and in the case of synchronous, the design, the basic difference is that all the flip-flops in the circuits are clocked simultaneously. Okay, these are the two basic designs that we are using in counter. Okay, first we will discuss the synchronous counting. And before that, if you want to design any sequential circuit, this is the normal procedure. You need to write the state diagram, okay, truth table, and then we need to implement the Boolean expression, and finally the circuit. Okay, so we can try this particular method to implement a 2-bit up counter, and by using a D flip-flop. And in order to implement a 2-bit up counter, we need the first state diagram. Means 2-bit up counter means we know that it's 0 0 0 1 1 0 1 1. So by using 2 bits, you can count from 0 to 3. So actually we need 2 flip-flops to implement 2-bit counter. Okay, so in the case of in this particular problem, we are using a D flip-flop to implement up counter. So we need 2 D flip-flops. So I can say that we require 2 D flip-flops to implement this. If it is 2-bit up counter, so if it's 3-bit up counter, we require a 3 D flip-flop. So this is a D flip-flop. This is another D flip-flop. Okay, and there will be 2 outputs, Q and Q bar. Here also Q and Q bar output will be there, and there will be clock signals. There are also clock signals. Okay, and in order to differentiate these 2 flip-flops, I can put a suffix D1. Here also Q1 and Q1 bar. This is D0, Q0, and Q0 bar. Okay, only to indicate 2 D flip-flops. So we can see that this is Q1 and this is Q0. So we need to generate a D flip-flop which generate this particular sequence. The first flip-flop should generate 0 1 0 1, and second flip-flop should generate 0 0 1 1 based on the clock signal. So now we can think about a state diagram. So there are actually 4 states for a 2-bit up counter. So we can say that state 1, I can put it as 0 0. Okay, that 0 0 is Q1 Q0. Okay, this is state 1, and from this particular state, when you apply clock, the counter module goes to 0 1. That's the next state. So this transition is indicating by clock. So when you apply clock, flip-flop output should go from 0 0 to 0 1. That is actually it is 0 0. Now we need to change it to 0 1 after application of this clock signal. And from the 0 1, it should go to next state after application of this clock. It should be 1 0. Okay, this is 0, this is 1 2, and when it is 1 0, and if you apply clock, it will go to next state, that is 1 1. Okay, this is the next clock signal. After application of this state clock signal, and if you apply one more clock, it will again go to 0 0. Okay, by using 2-bit maximum, you can count up to 1 1, and again if you operate this particular flip-flop, it will again go to 0 0, the initial state. So this is a state diagram of this particular 2-bit up counter. So this is a state diagram. Okay, similarly, if you are getting 3-bit, you will get 8 different states. So this is state 1, this is state, or I can state 0, state 1, state 2, state 3. Okay, S0, S1, S2, S3. 4 states are available for a 2-bit up counter. So now we got the state diagram. Now we need the truth table. So for example, you need present state and next state. So let it be Q1 and Q0 are the 2 present states. So for I can write 0 0 and 0 1 1 0 1 1. There are 4 possibilities for the state. Now you can consider the next state of after applying the each clock. If it is 0 0, the next state of the system, from 0 0, the transition goes to 0 1. So if the initial input is 0 0, the next state should be 0 1. Okay, and if it is 0 1, for example, this next state. If it is 0 1, the next state should be 1 0. That is 1 0. And if it is 1 0, next state is 1 1. And if it is in 1 1, the next state should be 0 0. So we need a circuit which will operate like this. If Q1 Q0 0 0, next state should be 0 1, etc. And now we need to complete this particular table by filling the last column. What should be the input to the flip-flops so that they can jump from present state to next state. Okay. So for that you need actually the excitation table, because initially this Q1 is 0. Now next state, let it be Qn. Okay, this is the nth state and this is the n plus 1 state. Okay, so this Q1 is changing to 0 to 0. So for that, the D1 flip-flops. So D1 flip-flop Q1 is initially 0. Next state is also 0. So for that, we need to identify what should be the D1. And from the excitation table, this is the excitation table of D flip-flop. The input is 0, present state is 0, and next state is 0. So for that, D input should be 0. So we can write it 0. And you can see that next Q1 is 1 initially, and next Q1 is 1. And for that, 0 to 1, to get a 0 to 1, the D input should be 1 from the excitation table. And from the third input, here it is 1 and here it is 1. Q1 is changing from 1 to 1. So if it is 1 to 1, the D input should be 1. And finally, it is from 1 to 0. To get 1 to 0, the D input should be 0. Okay. So we identified the D1 input should be 0, 1, 1, 0. Okay. Similarly, we need to identify what should be the changes that should occur in Q0. To identify that, we need to check the transition in Q0. So Q0 present state is 0 and next state is 1. So 0 to 1, to get 0 to 1, it should be 1. To get 1 to 0 change from the excitation table, 1 to 0, D input should be 0. Again, it's from 0 to 1, the input should be 1. And to get 1 to 0, the D input should be 0. So D0 should be 1 0 1 0. So now we got the truth table. So this is the second step. So we got the truth table. So this is stage 1 and this is stage 2. Now we need to implement the Boolean expression. So in order to get the Boolean expression, okay, so we need to write the Boolean expression now. Now we need to write the Boolean expression. Means we need an expression for D1, okay, in terms of Q1 and Q0. Okay, the available inputs are Q1 and Q0. By using this Q1 and Q0, we need to design D1. Okay, so if you compare this particular state, you can say D1 is equal to 1 for this particular combination, and so based on that, you can write one stage is 0 1, another one is 1 0. So you can write these two cases. So it is Q1 bar and Q0 in the first case, and second case it's Q1 and Q0 bar. So now we got an expression which is actually the XOR operation between Q1 XOR Q0. So in order to get a sequence like 0 1 1 0 in D1, so we need to connect the D1 input. Okay, so we need to connect the D1 input Q1 XOR Q0. Okay, and we need to design D0 now. So D0 should be to identify D0, this is one input and this is another one. So if you compare this, you will get Q1 bar and Q0 bar, and another case Q1 and Q0 bar. If you take Q0 bar as a common, it's Q0 bar, then Q1 bar plus Q1. Okay, so this become 1, so you can write Q0 bar. So now we got the final circuit. So this is a Boolean expression, so that step is okay. Now we need to implement the circuit. So for the implementing circuit, we need two flip-flops because there are two bit counter. Now we can make this connection. So D1 should be connected to uh, D1 should be Q1 XOR Q0. So this is Q1. So Q1 you can connect here. So this is Q1 and this is Q0. So we can take connection from Q1 and Q0, and we need to connect to an XOR gate. So this is an XOR gate, okay, and XOR gate output is connected to D, okay, and now we need to design D0. D0 should be equal to Q0 bar. So this is D0 actually. D0 should be Q0 bar. So this is Q0 and we need to connect this input to D0. Okay. Now this is a synchronous circuit, synchronous up counter. So we are designing synchronous up counter. So we need to connect same clock for both the seconds. So this is a rising edge clock we are connecting, or you can connect falling edge also. So assume there is a rising edge clock. So this is the final implementation of the circuit. So this circuit will produce the binary sequence, and if you take the output like this, Q1 and Q0. If we take output from Q1, this is Q1 and Q0, and if you apply different clock signals, based on that clock signal, when there is a rising edge, the Q1, Q0 output will be 0, 0, 0, 1, 1, 0, and 1, 1. Okay, it will produce output like this. Now we can see the waveform of that particular circuit. So during each clock cycle, initially it is 0, 0, now it is 0, 1, now it is 1, 0, 1, 1, after 1, 1 again it becomes 0, 0, then 0, 1, okay, again 1, 0, 1, 1, 0, 0. It will continue like this. If you apply more clocks, you will get the sequence repeated. So this is 0, this is 1, this is 2, 3, again 0, 1, 2, 3, 0, etc. So this is a sequence. Q1, Q0. Okay. Now we will discuss about the design of 2-bit down counter. So you already discussed up counter. Down counter means your combination will be like this. Initially it will be 1, 1. Next it will be 1, 0, and then it becomes 0, 1 and 0, 0. So it will be 3, 2, 1, 0. Or if you are starting from 2, it should be 1, then 0. After this 0, it again goes back to 1. Again, we need two flip-flop here because two output lines are required. So you can consider D0 and Q0, and here it is Q0 bar. Here it is Q1, and here it is Q1 bar. Okay, here it is D1. So two clock signals. Here also clock signals. So two flip-flops are required. So now we can write the state diagram here. State diagram means initially assume that if it is in the state 1, 1, okay, that is Q1, Q0 is 1, 1, and after application of the clock, it should go to the state 1, 0. Okay. Again, from this particular state, if you are applying any clock, it should go to state 0, 1. And after this, again, if you are applying any clock, it should go to another state. So from 0, 1, it goes to a state called 0, 0. And from this 0, 0, again, if you are applying any clock, it will go to the 1, 1 state. So this is a state diagram corresponds to 2-bit down counter, and we are going to design a synchronous down counter, okay, by using a D flip-flop. So here we need to write the truth table. Here it is Q1, Q0. And when you write the truth table, always use the sequential order. That will be easy to design. So Q1, Q0, we can you will get 4 different combinations: 0, 0, 0, 1, 1, 0, 1, 1. We know that this is a down counter, but you will get 4 different present state. So that present state you can write in the sequential order itself. Okay, and from this present state you can compare the next state. So now we need the next state. So assume that if the present state is 0, 0, what should be the next? What will be the next state? So if it is 0, 0, the next state will be 1, 1. So from 0, 0, it goes to 1, 1. And next you can see that if it is 0, 1, from 0, 1, it goes to 0, 0. So this is the next state. Okay. From state diagram, we can see that if the present state is 1 0, this is 1 0. From 1 0, it goes to 0 1, and from 1 1, if the present state, it goes to 1 0. So we got the present state and next state also. Now we need to take the excitation table of D flip flop. By using the excitation D flip flop, you need to identify what are the inputs. So what should be the inputs to the flip flop so that they jump from present state to next state. So we need to consider two inputs, D1 and D0. First we can consider D1. So here you can see that it's changing from 0 to 1. If it is changing from 0 to 1, the D1 input should be 1. And here it is Q1 change from 0 to 0, so D1 input should be 0. Here it is from 1 to 0, from the excitation table we know that it should be 0. And from 1 1, it's 1. Okay. Now we are getting D1. Similarly, we need to identify what will be the D0 input. So here it is 0 to 1, so D0 will be 1. Here 1 to 0, so it's 0. Again 0 to 1, it's 1. And here it is from 1 to 0, so it's 0. So now we are getting D1 and D0 inputs. So two tables, okay. Now we need to implement the Boolean expression. So in order to implement the Boolean expression, we need to design D1 in terms of Q1 and Q0. So for example, D1 is equal to 1. This is one case, this is another case. So Q1 Q0 bar plus another term is 1 1. So Q1 Q0. So we know that it's an XNOR gate. So Q1 XNOR Q0. Okay. And D0 we can design D0 again two combinations. Q1 bar Q0 is 1 plus another one is Q1 Q0 bar. Okay. Again you are getting Q0 bar as output. So now we need to implement the Boolean expression, implementing the circuit. So to implement that particular circuit, we know that D1 should be connected to output of Q1, Q0, XNOR. So we need an XNOR gate. Okay. So assume that this is an XNOR gate output, and the input of the XNOR gate is Q1 and Q0. Okay. Now we can say that D0 should be connected to Q0 bar. So Q0 bar is here. So we need to connect Q0 bar to D0. And this is a synchronous circuit. So we will connect the same clock signal for both D flip flops. And from this particular point, you can take output. This is Q1 output, and this is Q0. And this Q1 Q0 will produce 1 1 1 0 0 1 0 0. Okay. So implementation of the circuit. Now we can verify the waveform also. If it is 0 0 initially, next state is 1 1, so it is 3. Next will be 2. It will be, this is clock, and this is Q0, and this is Q1. And next state is 1, and next 0. Again 0 to 3 is 2 1 0. Okay. If it is starting from 0, next 3. If it is starting from 2, next state will be 1, like that. So this is a binary sequence. And this is all about 2-bit up counter and 2-bit down counter using D flip flop. And one more point is a synchronous circuit, because same clock is connected to both